Relativistic time dilation at near light speed. Time travel operates through extreme velocity approaching the speed of light. When an object moves at 99.999% of light speed, time dilation occurs where every second experienced by the traveler equals nearly 20 hours on Earth. This means a single day of travel at near light speed would propel you 197 years into the future while you age only 24 hours. The terrifying reality of this method lies in its irreversible nature. Once you accelerate to these speeds and return to Earth, everyone you knew would be dead. Your family, friends, and entire civilization could have collapsed and rebuilt multiple times. You become a temporal refugee with no way back to your original time period. The energy required to reach such speeds would equal the total power consumption of Earth for 3 months, making this journey a one-way ticket to an alien future. The physical effects on the human body remain unknown at these extreme velocities. Your mass would increase dramatically from an outside observer's perspective, potentially reaching 2 tons or the weight of a rhinoceros. The acceleration process itself could liquefy human tissue long before reaching the required speed. Gravitational time dilation near massive objects creates the second terrifying pathway for time travel. The intense gravitational field of a black hole warps spacetime so severely that time passes slower for anyone within the gravity well, compared to observers at a safe distance. Near a supermassive black hole's event horizon, hours could pass for the traveler while decades or centuries elapse elsewhere in the universe. The horror of this method stems from the spaghettification process. As you approach the black hole, the gravitational force on your feet becomes exponentially stronger than the force on your head. This tidal effect stretches your body vertically while compressing it horizontally, literally pulling you apart like taffy. Your bones would snap, your organs would rupture, and your consciousness would experience this torture in slow motion relative to outside observers. Even if you somehow survived the approach and used the time dilation effect, returning to normal spacetime presents an impossible challenge. The escape velocity from near a black hole's event horizon exceeds the speed of light. You would be trapped forever in this gravitational prison, watching the universe age rapidly around you through severely redshifted light while being slowly torn apart by tidal forces. The psychological trauma compounds the physical horror. You would witness the death of stars, the formation of new galaxies, and potentially the heat death of the universe itself, all while being unable to escape or communicate with the outside world. Wormhole time travel and exotic matter requirements. Wormholes represent the most theoretically viable method for backward time travel through Einstein-Rosen bridges. These hypothetical tunnels connect 2 separate points in spacetime, potentially linking different moments in time. To create a functional time machine, one end of the wormhole must be accelerated to near light speed and return to its original position. Due to time dilation, the accelerated end experiences time more slowly than the stationary end. When reconnected, one mouth exists in the past relative to the other. The terrifying aspect of wormhole travel lies in the exotic matter requirement. Keeping a wormhole stable and traversable demands exotic matter with negative energy density, a substance that has never been observed in nature. This material would need to possess properties that violate our understanding of physics, potentially creating regions where energy flows backward and causality breaks down. The journey through a wormhole itself presents unknown horrors. The tunnel could collapse instantaneously, crushing the traveler into a singularity. Quantum fluctuations within the wormhole might tear apart molecular bonds, disintegrating any matter that attempts passage. The exotic matter lining the wormhole walls could interact with human tissue in ways that fundamentally alter atomic structure, potentially transforming the traveler into an unrecognizable form of matter. Even successful passage offers no guarantee of survival. The destination could be a region of space with lethal radiation, extreme temperatures, or gravitational fields that immediately destroy any biological matter. Cosmic string time loops and spacetime defects. Cosmic strings are hypothetical, one-dimensional defects in spacetime formed during the early universe's phase transitions. These theoretical structures possess extraordinary density, containing the mass of entire galaxies compressed into threads thinner than atomic nuclei. When 2 cosmic strings move past each other at near light speed, or when one moves rapidly alongside a massive object, they warp spacetime to create closed time-like curves that loop back through time. The terror of cosmic string time travel begins with their detection impossibility. These invisible defects could exist anywhere in the universe, creating temporal anomalies without warning. A spacecraft accidentally encountering intersecting cosmic strings could be flung backward in time against the crew's will, trapping them in a temporal prison with no escape mechanism. The gravitational effects of cosmic strings would be catastrophic for human travelers. The intense space-time curvature required to form closed time-like curves would generate tidal forces millions of times stronger than those near black holes. Human bodies would be instantly vaporized, with individual atoms torn apart by the extreme gravitational gradients before any time travel could occur. The quantum instability surrounding cosmic string intersections creates additional horrors. Virtual particles would spontaneously materialize and annihilate in violent bursts of radiation. The fabric of space-time itself becomes unstable, potentially creating regions where the laws of physics cease to function normally, leaving travelers in a realm where matter and energy behave in incomprehensible ways. Tipler, cylinder rotation, and infinite mass requirements. The Tipler cylinder represents a theoretical time machine involving a massive, infinitely long cylinder spinning at near-light speed. This construct, proposed by physicist Frank Tipler, would twist space-time around itself so severely that closed time-like curves form, allowing objects to loop through time and arrive in the past. The cylinder must contain at least 10 times the mass of our Sun compressed into an infinitely long structure rotating billions of times per minute. The horrifying reality of approaching a Tipler cylinder begins with the rotational forces. The cylinder's surface would move at nearly 300,000 kilometers per second, creating gravitational frame-dragging effects that would shred any approaching spacecraft. The centrifugal forces alone would pulverize matter into subatomic particles long before reaching the time travel trajectory. The infinite length requirement presents an existential nightmare. Any finite version of the cylinder would collapse under its own gravity, creating a black hole that consumes everything within light years. The construction would require more matter than exists in observable galaxies, demanding the destruction of countless star systems and civilizations to gather sufficient mass. Even theoretical success offers no safety. The time traveler must follow a precise spiraling path around the cylinder while being bombarded by deadly radiation from the spinning supermassive object. A single miscalculation would send the traveler into the cylinder's surface at relativistic speeds, resulting in instant annihilation. The temporal destination remains uncontrollable, potentially depositing survivors in the vacuum of space billions of years before Earth's formation. Bootstrap Paradox and Causality Violations. The Bootstrap Paradox represents one of the most psychologically terrifying aspects of backward time travel, creating objects or information with no discernible origin. In this scenario, a time traveler receives information from their future self, uses that knowledge to invent something, then travels back to give themselves the same information. The knowledge exists in an endless loop with no original creator, violating our fundamental understanding of cause and effect. The horror lies in the complete erasure of free will and personal agency. If you receive a letter from your future self containing lottery numbers, use those numbers to win. Then travel back to deliver the letter to your past self, who wrote the numbers originally. The information appears to exist outside normal causality, suggesting that your choices were never truly your own but predetermined by temporal loops beyond your control. This paradox extends to technological advancement and human knowledge. Scientific breakthroughs, artistic creations, and philosophical insights could all originate from bootstrap loops, meaning humanity's greatest achievements might have no actual human creator. The implication suggests that consciousness itself could be trapped in predetermined patterns, with every thought and decision already mapped out in temporal loops that stretch across eternity. The psychological trauma of discovering you exist within a bootstrap paradox would be devastating. Every memory, relationship, and accomplishment becomes suspect, potentially nothing more than predetermined events in an endless cycle where genuine human creativity and choice are illusions. Grandfather Paradox and Timeline Destruction. The Grandfather Paradox represents the most catastrophic threat posed by backward time travel, potentially unraveling the entire fabric of reality. This paradox occurs when a time traveler kills their own grandfather before their parent is conceived, creating a logical impossibility where the traveler simultaneously must and cannot exist. The paradox extends beyond family relationships to any action that prevents the time traveler's original motivation for traveling backward. The terrifying implications suggest that successful backward time travel could trigger a cascade failure throughout spacetime itself. If the universe cannot resolve the logical contradiction, reality might collapse into quantum superposition states where multiple conflicting timelines exist simultaneously. Matter and energy could become unstable as the fundamental laws of causality break down, potentially erasing entire galaxies from existence. Some physicists propose that the universe would violently correct these paradoxes through quantum mechanical processes. This correction might manifest as spontaneous explosions, reality storms, or temporal shockwaves that propagate outward from the paradox point at light speed. Civilizations across the cosmos could be instantly annihilated, as the universe rewrites itself to maintain causal consistency. The psychological horror compounds when considering that the time traveler might retain memories of the original timeline while existing in the corrected version. They would remember people who never existed, events that never occurred, and relationships that were erased from reality. This temporal amnesia could drive the traveler to complete madness as they struggle to distinguish between authentic memories and phantom recollections from deleted timelines. Quantum entanglement, retrocausality, and information paradoxes. Quantum entanglement creates the possibility of retrocausality, where measuring one particle instantly affects the past state of its entangled partner regardless of distance. Some interpretations of quantum mechanics suggest that information could influence past quantum events, creating a form of backward time travel that operates at the subatomic level. This phenomenon challenges classical cause and effect by allowing future measurements to determine past particle states. The terror of retrocausal quantum effects lies in their undetectable nature and potential for reality manipulation. If consciousness can influence quantum measurements, then sufficiently advanced beings might alter past events by manipulating entangled particles in the present. Entire histories could be rewritten without anyone's knowledge, as the changes would propagate backward through quantum connections that exist outside normal spacetime. The implications for human free will become nightmarish when considering that every decision might be influenced by future quantum measurements. Your thoughts and choices could be predetermined by quantum entanglement networks stretching across time, making you a puppet controlled by future versions of yourself or other conscious observers. The boundary between past, present, and future dissolves into a web of quantum correlations where causality becomes meaningless. Most disturbing is the possibility that retrocausal effects are already occurring around us constantly. Every quantum measurement in laboratories worldwide might be altering past events in subtle ways, gradually reshaping history through accumulated microscopic changes. Reality itself could be unstable, constantly shifting as quantum experiments inadvertently rewrite the past through entanglement connections that span the entire universe. Closed time-like curves and rotating black holes. Rotating black holes, described by the Kerr metric, contain a region called the ergosphere, where space-time is dragged around by the black hole's rotation. Within certain solutions to Einstein's field equations, this rotation creates closed time-like curves that loop back on themselves, theoretically allowing time travel to the past. These curves exist in the region between the event horizon and the static limit, where space-time itself rotates faster than the speed of light. The horror of navigating closed time-like curves begins with the ergosphere's lethal environment. The rotating space-time drags everything within it, making it impossible to remain stationary relative to distant observers. Travelers would be forced to orbit the black hole at tremendous speeds while being bombarded by high-energy particles and radiation from the accretion disk. The tidal forces would stretch and compress the human body with each orbit, causing excruciating pain before inevitable death. The temporal mechanics create additional nightmares for any survivor. Following a closed time-like curve means experiencing the same events repeatedly in an endless loop, potentially for eternity. The traveler might witness their own death countless times, retain memories of infinite previous loops, or become trapped in a temporal prison where escape is physically impossible due to the curve's closed nature. Most physicists believe quantum effects would destroy these curves before they could be traversed, creating a firewall of virtual particles that would incinerate any approaching matter. The quantum vacuum becomes unstable near closed time-like curves, spontaneously generating particle pairs with enough energy to vaporize atomic nuclei and prevent any macroscopic time travel from occurring. The WOW signal. On August 15, 1977, the Big Ear Radio Telescope in Ohio detected a powerful, narrowband radio signal from the direction of the constellation Sagittarius. Volunteer astronomer Jerry Eman found the sequence 6EQUJ5 in the data printout, circled it, and wrote "WOW" in the margin. 4 properties made it extraordinary. Its intensity was 30 times higher than the background noise, eliminating the possibility of a random statistical fluctuation. Its frequency was near the hydrogen line at 1420 MHz, a universal reference point in radio astronomy, long considered a likely channel for interstellar communication. It was extremely narrowband, less than 7 parts per million in fractional width, something no known natural source produces, and it lasted 72 seconds. Exactly the duration expected for a continuous source being swept over by Earth's rotation. What makes the WOW signal unsettling is the implication behind its properties. The signal was consistent with a highly focused, high-powered artificial transmission, something far beyond our own long-range radio capabilities in 1977. If it did originate from an intelligent source, it would mean there is, or was, a civilization capable of intentionally directing enormous amounts of energy across interstellar distances with extreme precision. Such a civilization would almost certainly be far more advanced than humanity, raising questions about their technological reach, motives, and awareness of our existence. The fact that the signal appeared once and never repeated compounds the unease. It suggests a fleeting glimpse of something vast and unreachable, a message we were never meant to answer, or evidence of an intelligence that could contact us at will but chooses not to. This combination of capability, unknown intent, and complete silence makes it one of the most disturbing scientific mysteries in history. The 22-minute signal. In 2022, astronomers using the Murchison Wide Field Array detected a radio source unlike any previously seen. The object, designated GPM J183910, produces powerful radio pulses roughly every 22 minutes, each lasting between 30 seconds and 5 minutes. Follow-up analysis revealed the signal had been appearing in archival observations since at least 1988, maintaining extraordinary rotational stability over 35 years. This is highly unusual. Pulsars, the neutron stars normally responsible for such emissions, gradually lose rotational energy and slow down measurably over time. If the source is a neutron star, it rotates far slower than any known pulsar that still produces radio emissions once every 1,318 seconds and lies deep within the theoretical death valley, where pulsars are expected to be inactive. Yet the radio emission is bright, polarized, and exhibits characteristics consistent with the electron-positron pair production cascades that generate pulsar beams. No known pulsar model explains both the slow rotation and the long-term stability. Alternative explanations include a highly magnetic white dwarf, or a magnetar, undergoing a prolonged outburst. A magnetar starquake could, in principle, reignite a dead pulsar beam, but such events fade within years, not decades, and are usually accompanied by detectable X-ray emission, which is absent here. A white dwarf could rotate this slowly and remain stable, but would require an unprecedentedly strong magnetic field and luminosity thousands of times greater than any white dwarf radio source observed to date. The inability of current neutron star or white dwarf models to account for GPM J183910 makes it one of the most perplexing signals in modern radio astronomy. Its steady beacon challenges fundamental theories of how compact stellar remnants evolve and emit radiation. Astronomers suspect similar objects may be hidden in existing survey data, and each new detection will push the limits of our understanding of stellar physics. The perytons. Between 1998 and 2015, the Parkes Radio Observatory in Australia detected a series of short, bright bursts of radio waves that appeared a few times each year. These events, nicknamed perytons after a mythical creature, were puzzling because their characteristics did not match known astronomical phenomena. They were strongest in the 2.4 GHz range, occurred mostly during the day, and seemed to originate from within about 5 kilometers of the telescope itself. For years, researchers considered possibilities such as high-altitude lightning or other atmospheric electrical events. The mystery was solved in January 2015 when a new interference monitor was installed. It revealed that perytons were caused by microwave ovens on site. When the oven door was opened before the timer reached 0, the magnetron inside would continue emitting a short burst of radio waves for a few milliseconds. If the telescope happened to be aimed in the right direction, This emission would be detected as a false astronomical signal. While this discovery resolved the perytons without invoking any cosmic source, it served as a cautionary example. Signals that appear mysterious or alien can sometimes have very mundane origins, and every possible terrestrial explanation must be excluded before a deep space source is considered. Fast radio bursts. Fast radio bursts, or FRBs, are intense, millisecond-long flashes of radio energy that originate far beyond our galaxy. The first known example was discovered in 2007 when Duncan Lorimer and his team analyzed archival data from the park's observatory and found a burst lasting just 5 milliseconds from a location near the Small Magellanic Cloud around 3 billion light-years away. In that fraction of a second, the burst released as much energy as the Sun emits over 80 years. FRBs occur without warning and show no consistent pattern, making them difficult to detect. Most have been observed only once, but a few repeat, allowing more detailed study. The sources remain uncertain, but leading hypotheses include cataclysmic events such as neutron stars collapsing into black holes, collisions between neutron stars, or flares from magnetars, neutron stars with extremely strong magnetic fields capable of producing bursts of high-energy radiation. Their sheer energy output makes FRBs unnerving. To generate that much power in such a short time requires astrophysical conditions among the most extreme in the universe. If an artificial source were responsible, it would imply a technology operating on a scale that dwarfs anything humanity can produce, potentially harnessing the energy of entire stars. Combined with the randomness of their occurrence, FRBs represent a phenomenon we cannot predict, control, or fully explain, making them one of the most enigmatic and unsettling signals ever detected from space. The Lorimer burst. The Lorimer burst is the name given to the first recorded fast radio burst, detected in 2007 by Duncan Lorimer and his student David Narkovic while reviewing data from the park's radio telescope. The event itself had occurred in 2001 and lasted only a few milliseconds, yet its strength indicated it had come from well beyond our galaxy. This single detection revealed the existence of an entirely new class of astrophysical phenomena. Analysis showed that the Lorimer burst dispersion, the delay of lower-frequency radio waves compared to higher ones, matched what would be expected if the signal had traveled through vast amounts of intergalactic plasma. Its energy output was immense, rivaling the Sun's total emission over many days. Compressed into a blink of time, no nearby object or terrestrial interference could account for it, confirming its extragalactic origin. The discovery was alarming for two reasons. First, it hinted that there may be countless similar bursts occurring across the universe, but almost all go undetected due to their brief and unpredictable nature. Second, the power and compactness of the event require conditions that push the limits of our astrophysical understanding, involving either the catastrophic destruction of massive stellar remnants or unknown processes capable of producing concentrated energy on a galactic scale. It opened an entirely new mystery in radio astronomy, one with no definitive answers to this day. BLC-1 signal. On April 29, 2019, the Breakthrough Listen project detected a narrowband radio signal at 982 MHz using the Parkes Murray-Yang radio telescope in Australia. Designated BLC-1, short for Breakthrough Listen Candidate 1, it was found during observations of Proxima Centauri, the closest star to the Sun. The signal's characteristics, its narrow frequency range and apparent drift, consistent with a moving source, were initially intriguing because they matched what might be expected from an artificial transmitter. BLC-1 persisted for several hours and was not immediately linked to any known satellite or terrestrial source. Its detection triggered an extensive verification process, outlined in a peer-reviewed Nature Astronomy article. Researchers compared the signal against a large database of known interference sources and examined whether it repeated during later observations. No recurrence was found, and further analysis revealed subtle features indicating the signal most likely originated from human-made radio interference rather than from Proxima Centauri. The unsettling element in the BLC-1 case is how closely it resembled a plausible extraterrestrial technosignature before being ruled out. It demonstrated that even with modern verification methods, a signal can pass multiple initial filters and still ultimately have a mundane explanation. For many researchers, this reinforced both the difficulty and the tension in the search for extraterrestrial intelligence. Any genuine detection could initially look just like BLC-1, leaving us uncertain whether we had glimpsed the first confirmed message from another civilization or simply another artifact of our own technological noise. Now, you got the scariest signals, but there is a lot scary things out there. Check this video of the scariest places in the universe. The Boötes Void. The Boötes Void is one of the most profoundly empty and eerie structures ever found in the universe. Discovered in 1981 by a team of astronomers led by Robert Kirshner during a redshift survey of galaxies. Located roughly 700 million light-years from Earth in the direction of the Boötes constellation, it stunned researchers with its sheer absence of galaxies. The void stretches approximately 330 million light-years in diameter. To contextualize this scale, the Milky Way galaxy is about 100,000 light-years in diameter. That means you could place more than 2,000 Milky Ways side by side across the Boötes void. Its volume is estimated at over 236 billion cubic light-years. If the United States were projected into this space, it would fit more than 2 billion times over, making it one of the largest known structures of emptiness in the observable universe. What makes the Boötes void so profoundly unsettling is not just its size, but the level of emptiness it contains. In a region of that volume, scientists would typically expect to find around 2,000 galaxies based on standard cosmic density. Instead, fewer than 60 galaxies have been detected. That's less than 3% of what should be there. It's not just underpopulated, it's a cosmic desert on an incomprehensible scale. One of the prevailing theories suggests that the void was created by the gravitational merging of several smaller voids early in the formation of the universe. This would have left behind a massive bubble of near-total nothingness. However, this theory doesn't fully explain the scale of the void, nor why it's so geometrically smooth. The Boötes void is terrifying, not because it's dangerous, but because it challenges everything we think we know about the structure of the cosmos. It suggests that the universe might contain regions completely cut off from galactic activity places, where, if you were placed inside, there would be no visible light in any direction, no stars, no galaxies, no cosmic radiation strong enough to illuminate the dark. From a human perspective, it's one of the most extreme expressions of cosmic isolation ever discovered, a reminder that the universe is not uniformly vibrant, but stitched together with patches of pure, silent, endless void. The Eridanus supervoid. The Eridanus supervoid is one of the most bizarre and colossal voids ever identified. First identified in 2004 by astronomers studying data from the Wilkinson Microwave Anisotropy Probe, which maps the cosmic microwave background, the faint afterglow of the Big Bang. In the direction of the Eridanus constellation, they noticed a large cold spot, significantly cooler than surrounding regions of the sky. Further investigation revealed that this wasn't just a temperature anomaly, it coincided with a massive underdense region in space. Located approximately 1.3 billion light-years away, the Eridanus supervoid is believed to span nearly 1 billion light-years across, making it one of the largest voids ever discovered. For scale, a beam of light would take 1 billion years to travel from one end to the other, which is more than 7 times the current age of multicellular life on Earth. And if a single banana were 20 centimeters long, it would take 5 quintillion bananas to stretch across the Eridanus supervoid. Unlike typical voids, which are already sparse, this supervoid stands out for its extreme size and the depth of its emptiness. It contains significantly fewer galaxies than expected for a region of that magnitude. What makes it so disturbing is the potential connection between this void and the cold spot in the CMB. Some scientists theorize that light traveling through the underdense region loses energy, creating the cold spot via the integrated Sachs-Wolf effect. However, this explanation is not universally accepted. The phenomenon remains scientifically controversial, leaving room for alternative interpretations, including ones that extend beyond the boundaries of known physics. Some speculative theories suggest the Eridanus supervoid could be evidence of a collision with another universe, or the result of unknown large-scale forces at work. Even in more conservative models, its vast emptiness forces cosmologists to confront the possibility that our understanding of how matter distributed itself after the Big Bang might be incomplete. The Eridanus supervoid is terrifying, not because of what we know about it, but because of what we don't. It's a billion light-year-wide question mark stitched into the fabric of the universe, defying conventional structure and hinting at forces that may exist far outside our current comprehension. The Great Attractor. The Great Attractor is a gravitational anomaly so powerful that it's redirecting the paths of entire galactic superclusters, including our own. First detected in the late 70s and early 80s, not by direct observation, but through its gravitational influence on galaxies. Astronomers noticed that the Milky Way and hundreds of thousands of other galaxies were all moving toward a specific region of space at a speed of approximately 600 kilometers per second, fast enough to travel from Earth to the Moon in 11 minutes. This mysterious pull couldn't be explained by any known mass within the visible universe at the time. The problem was that the source of this immense gravitational force lies behind the zone of avoidance, a region obscured by the dense gas, dust, and stars of our own Milky Way galaxy. This made it incredibly difficult to observe directly using optical telescopes. The region itself is located about 150 to 250 million light-years away. To put this in scale, the light currently reaching us from the Great Attractor started its journey around the time early dinosaurs appeared on Earth, near the constellation Norma, at the center of the Laniakea supercluster, which includes our Milky Way. What makes the Great Attractor so terrifying is that we are influenced by a force we cannot see. It's a gravitational anomaly, possibly a supermassive concentration of galaxies and dark matter, dragging entire galaxy clusters, including ours, toward it. Later studies identified the Norma cluster as a key contributor, but the full structure and scope of the Great Attractor remain hidden. Adding to the unsettling mystery, some scientists believe that the Great Attractor is itself being pulled toward an even larger and more massive structure, the Shapley supercluster, which lies farther away in the same general direction. This recursive pattern structures pulling on structures reveals a cosmic tug-of-war that we don't fully understand. The horror of the Great Attractor lies in its invisibility and scale. It's not a place we can travel to or observe directly with ease, yet it exerts force across hundreds of millions of light-years, dragging entire galactic systems like leaves in a current. From a human perspective, it represents the existential terror of being caught in the flow of a universe guided by unseen forces that may never be completely revealed. Gamma-ray bursts. Gamma-ray bursts are among the most violent and destructive events ever observed in the universe. First detected in the late 1960s by military satellites monitoring nuclear tests, these sudden, high-energy flashes of gamma radiation have since become a central focus of astrophysical research. They occur unpredictably, last anywhere from milliseconds to several minutes, and release more energy in a few seconds than our Sun will emit in its entire 10 billion-year lifetime. That's the equivalent of 100 billion trillion nuclear bombs detonating at once. Long-duration GRBs can release as much energy as the entire Milky Way galaxy produces in a year, all focused into a narrow beam. What makes GRBs so terrifying is not just their sheer power, but their reach. A long-duration GRB, typically caused by the collapse of a massive star into a black hole, can send a collimated jet of radiation across vast stretches of space. If Earth were ever caught within such a beam from a nearby source, the results would be catastrophic. The gamma radiation would strip away the ozone layer, flood the planet with lethal UV rays, and likely trigger a mass extinction event. Some researchers even speculate that a GRB may have contributed to past extinction events in Earth's history. GRBs are divided into two primary types: long-duration bursts linked to hypernovae, and short-duration bursts thought to result from neutron star collisions. Both scenarios are catastrophic, but it's the unpredictability and intensity of the beams they emit that elevate them to one of the most frightening cosmic threats. We can't see GRBs coming. They arrive without warning and are often observed only after the damage would already be done. There's no known way to shield a planet from their effects, and they can originate from galaxies billions of light-years away, making them one of the few threats capable of causing devastation from unimaginable distances. The event horizon. The event horizon is not a place in the traditional sense, but a boundary in space-time surrounding every black hole. It was first described mathematically by Carl Schwarzschild in 1916, following Albert Einstein's publication of General Relativity. This invisible perimeter marks the point at which gravity becomes so intense that nothing, not even light, can escape. Once crossed, return is impossible. The event horizon is not a surface or a wall. It has no physical structure. It is a mathematical threshold, a point of no return. Anything that passes this boundary is irrevocably pulled inward toward the black hole's center, toward the singularity. From the outside, an object falling into a black hole appears to slow down, freeze, and fade as it approaches the event horizon due to time dilation. From the object's own perspective, it crosses the boundary quickly and is stretched, compressed, and ultimately destroyed by tidal gravitational forces, a process known as spaghettification. The terror of the event horizon lies in its finality. It is the edge of causality. No signals can pass from inside to out, no observations can be made beyond it. In essence, it marks the limits of physical law as we know it. Space and time lose meaning beyond the event horizon, and our mathematical tools no longer function. We never actually observed an event horizon until 2019, when the Event Horizon Telescope released the first direct image of the shadow of a black hole in galaxy M87, located 53 million light-years away. What we saw was not the event horizon itself, but its shadow, a circular region surrounded by glowing gas being pulled into darkness. What makes the event horizon one of the scariest places in the universe is its role as a cosmic point of erasure. It is where the known ends and the unknowable begins. A frontier not just of space, but of reality, where even information, the bedrock of physics, may be destroyed. The singularity. At the heart of every black hole lies the singularity, a single point where mass is compressed into infinite density. While the concept of black holes was derived from Einstein's theory of general relativity in the early 20th century, the singularity itself was more rigorously defined in the 1960s through the work of Roger Penrose and Stephen Hawking. Unlike the event horizon, which can be observed indirectly, the singularity remains completely hidden and inaccessible to observation. The singularity is where all known laws of physics break down. General relativity, which governs the behavior of gravity on large scales, predicts infinite curvature of spacetime at this point. At the same time, quantum mechanics, which governs the behavior of particles at the smallest scales, has no way to describe or handle this infinite density. There is no unifying theory that can explain what happens here. This is known as the problem of quantum gravity. Inside the event horizon, every path in space leads inevitably toward the singularity. No matter what direction you move, space-time itself funnels you toward the center. As an object approaches, it is subjected to intense gravitational gradients. These tidal forces become so extreme that they stretch and compress matter until it is destroyed. From a scientific standpoint, the singularity is not just a place, it is the breakpoint of reality. Concepts such as time, space, causality, and physical existence become meaningless. This isn't just a theoretical flaw in our models. It is a real, physical destination that may exist in the cores of countless black holes throughout the universe. What makes the singularity so terrifying is that it embodies the limits of human knowledge. It is the point where mathematics ceases to function, where observations cannot be made, and where even the fabric of space-time collapses into something we don't understand. For humanity, the singularity is not only a destructive gravitational abyss, it is the ultimate unknown. Sagittarius A star. Sagittarius A star is a supermassive black hole located at the very center of the Milky Way galaxy, approximately 26,000 light-years from Earth in the direction of the Sagittarius constellation. Its existence was first suspected in the 1970s, due to strong radio emissions detected in that region. In 1974, astronomers Bruce Ballack and Robert Brown officially identified Sagittarius A star as a compact radio source using the National Radio Astronomy Observatory. The black hole is estimated to have a mass of about 4 million times that of the Sun. Yet, it is confined to a region no larger than our solar system. Its gravitational influence is so powerful that it affects the orbits of nearby stars, particularly a group of fast-moving stars known as S-stars, which orbit the black hole at incredibly high speeds. This motion provided some of the clearest indirect evidence of its existence long before direct imaging was possible. In 2022, the Event Horizon Telescope released the first ever image of Sagittarius A star's shadow, confirming visually what decades of radio and infrared data had strongly indicated: that a supermassive black hole lies at the heart of our galaxy. What makes Sagittarius A star so uniquely frightening is its proximity. While many of the universe's most dangerous objects are billions of light-years away, Sagittarius A star resides at the core of our own galactic home. Its event horizon marks the boundary beyond which anything, including light, matter, and even information, is lost forever. Anything that crosses this boundary spirals toward the singularity at its center. Though Earth is currently far enough away to remain unaffected, Sagittarius A star serves as a constant reminder of the quiet but destructive forces operating within our own galaxy. It is capable of devouring stars, warping time, and altering the structure of surrounding space. Should it ever become more active, say, by absorbing a dense cloud of matter, it could release powerful bursts of radiation with galactic consequences. Sagittarius A star represents a cosmic predator hiding in plain sight. It is dormant, invisible in regular light, and largely silent, yet it exerts gravitational control over everything in our galaxy. Its presence is a chilling demonstration that even the heart of the galaxy is ruled by forces we can barely comprehend. The Big Rip. The Big Rip is one of the most haunting theoretical endings to the universe, an ultimate doomsday scenario driven not by fire, cold, or collapse, but by the relentless acceleration of cosmic expansion. First proposed in the early 2000s, the theory stems from the observation that the universe isn't just expanding, it's expanding faster over time, propelled by a mysterious force known as dark energy. What makes the Big Rip so terrifying is the implication that this acceleration might not level off or slow down. It could continue increasing indefinitely. If dark energy's influence grows stronger over time, then its repulsive force could eventually overcome every form of gravitational, electromagnetic, and even nuclear binding. Structures we consider permanent galaxies, stars, planets, atoms, would be systematically torn apart. It starts slowly. Galaxies drift further from one another. Then, galaxy clusters disband. In the final moments, solar systems are pulled apart, planets ripped from their orbits, and stars torn into fragments. Closer to the end, even atoms are no longer safe. Molecular bonds break, protons and neutrons dissolve. The fabric of matter itself disintegrates. In the last instance, before the final rip, space-time stretches infinitely fast. The laws of physics break down not at a single point, but everywhere, all at once. The Big Rip isn't just an ending, it's an unraveling. A scenario where the universe doesn't collapse into a singularity or fade into heat death, but tears itself to shreds from within. And the most chilling part? We don't know yet if it's coming. The strength and behavior of dark energy remain one of the biggest unknowns in cosmology. If it continues to accelerate unchecked, the Big Rip could be billions of years away, or, in a far more unstable model, it could occur sooner than we expect. The Big Rip represents a uniquely unsettling fate. Not a bang, not a freeze, but a cosmic shredding, where everything we know is ultimately unmade by the very thing that keeps the universe growing. Quasars. Quasars, short for quasi-stellar radio sources, were first discovered in the early 1960s, when astronomers detected strange points of light that appeared star-like but emitted radio waves, and exhibited extreme redshifts, indicating they were incredibly far away. The first confirmed quasar, 3C273, was identified by Martin Schmidt in 1963. It became clear that these were not stars at all, but the extremely bright and energetic cores of distant galaxies powered by supermassive black holes. At the center of each quasar lies a black hole millions to billions of times the mass of the Sunday. As gas, dust, and even stars spiral into the black hole, they form an accretion disk that heats up through friction to millions of degrees, emitting radiation across the electromagnetic spectrum. Quasars are capable of outshining entire galaxies. Some release 1,000 times more energy than all the stars in the Milky Way combined. The terrifying aspect of quasars is their raw, destructive power. The radiation they produce, especially in X-ray and ultraviolet, can travel across billions of light years. Their relativistic jets, launched from the poles of the spinning black hole, can stretch for millions of light years, acting like cosmic blowtorches that strip gas from galaxies and sterilize any planetary systems caught in their path. Fortunately, most quasars are located in the early universe. Because they formed billions of years ago, their light is only now reaching Earth. Today, fewer quasars are active because their central black holes have consumed most of the available matter. But the fear remains. If a quasar were to form near our galaxy, its radiation would wipe out Earth's atmosphere, render the planet uninhabitable, and disrupt or destroy any trace of life. We are lucky that the few quasars visible from Earth are billions of light years away, because up close, they are among the most hostile environments the universe can produce. Magnetars. Magnetars are a rare and extremely dangerous type of neutron star, first theorized in the early 1990s and confirmed through the observation of unusual gamma-ray bursts known as soft gamma repeaters. These compact stellar remnants are formed when a massive star undergoes a supernova explosion, leaving behind a dense core that collapses into a neutron star. In the case of magnetars, this remnant develops an ultra-powerful magnetic field, making it one of the most extreme objects in the cosmos. A typical neutron star already compresses more mass than the Sun into a sphere only about 20 kilometers across, but a magnetar's magnetic field is what sets it apart. It can be up to a quadrillion times stronger than Earth's magnetic field. This kind of magnetic intensity is not just theoretical, it's so strong that if a magnetar were located as far as the Moon, it could wipe every credit card on Earth, disrupt all electronic devices, and even distort atomic structure. What makes magnetars terrifying isn't just their power, it's their instability. Their magnetic fields twist and fracture the star's crust, occasionally releasing massive bursts of X-rays and gamma rays in a fraction of a second. One such flare in 2004, from a magnetar called SGR 1806-20, released more energy in 0.2 seconds than the Sun emits in 250,000 years. If it had been only a few light years closer, it could have devastated Earth's atmosphere. Magnetars are unpredictable, violent, and very poorly understood. They don't announce themselves with visible light or heat, but with sudden, invisible radiation blasts that could fry spacecraft and cripple global infrastructure if one ever formed too close. There are currently about 30 known magnetars, most of them thousands of light years away. But given how difficult they are to detect, astronomers believe there could be many more lurking throughout the galaxy. If even one were to activate within dangerous range, it could become a cosmic weapon, an invisible bomb in the sky detonating without warning. The dark flow. The dark flow is one of the most mysterious and unsettling large-scale phenomena in cosmology. It was first detected in 2008 by astronomers using data from NASA's Wilkinson Microwave Anisotropy probe. The researchers observed that clusters of galaxies were all drifting in the same direction, toward a specific region of the sky, at velocities exceeding 600 kilometers per second without any identifiable cause. What makes the dark flow so alarming is that this motion cannot be explained by any known gravitational structure within the observable universe. Galaxy clusters as far as 2.5 billion light-years away are all being pulled in the same direction. Yet nothing in that region, no superclusters, voids, or anomalies appears massive enough to account for the effect. Some scientists believe this might point to the existence of a massive structure beyond the edge of the observable universe, something so enormous and influential that it tugs on galaxy clusters across billions of light-years. Others have speculated more radically that it could be evidence of a multiverse, a realm beyond our known universe, exerting a gravitational pull we cannot see. The unsettling part of the dark flow is its implication that the universe may be larger, stranger, and more dangerous than we ever imagined. If this effect is real and not an observational error, it suggests that unseen forces outside our cosmic horizon are interacting with our universe. We can't see them, measure them directly, or understand them using current models of physics. To this day, the dark flow remains a subject of debate. Some studies using newer data, like the Planck satellite, have failed to reproduce the original results, while others continue to find hints of consistent movement. But the possibility that something unknown, possibly outside of space-time as we know it, is pulling on the largest structures in the cosmos is enough to make it one of the scariest ideas in modern astrophysics. Rogue black holes. Rogue black holes are solitary black holes that drift through space untethered to any galaxy, invisible and silent. While black holes are typically found at the centers of galaxies or within stellar systems, rogue black holes are ejected from their host galaxies through powerful events such as galactic collisions, gravitational interactions, or the violent collapse of massive stars. Their theoretical existence has long been accepted, but it wasn't until 2022 that NASA confirmed the first potential detection of a rogue black hole about 5,000 light-years from Earth using gravitational microlensing. What makes rogue black holes terrifying is their complete stealth. They do not emit light, radiation, or any electromagnetic signals unless interacting with nearby matter. Without accretion disks or surrounding material, they are effectively invisible to conventional observation techniques. The only way to detect one is through the way it bends and magnifies the light of background stars, an effect that requires precise alignment and is extremely rare to observe. Once ejected from a galaxy, a rogue black hole can wander through interstellar or intergalactic space for billions of years. If one were to pass through a star system, it could disrupt planetary orbits, tear apart stars, or even swallow entire planets, all without warning. Earth would have no way of detecting its approach until gravitational effects began to distort space locally, and by then, it would be too late to escape. Estimates suggest that the Milky Way alone could harbor millions of these rogue black holes, silently roaming the galactic outskirts or even passing through the disk unnoticed. Because they are black holes without an anchor, they represent cosmic bullets, traveling blindly through space and capable of total destruction without a trace. What makes them among the scariest phenomena in the universe is their combination of power and unpredictability. A rogue black hole doesn't announce itself. It doesn't shine. It simply moves quietly, invisibly, and obliterates anything in its path. TON 618 is one of the most powerful and terrifying objects ever discovered in the known universe. It was first cataloged in the 1950s during a survey of blue stellar objects, but its true nature wasn't understood until the 1970s, when astronomers realized it wasn't a star at all. It was a quasar, powered by a supermassive black hole of unimaginable proportions. Located approximately 10.4 billion light-years away, TON 618 is so distant that we see it as it existed just a few billion years after the Big Bang. At its center lies a black hole with an estimated mass of around 66 billion solar masses, making it one of the largest and most massive black holes ever detected. For comparison, the supermassive black hole at the center of the Milky Way, Sagittarius A, is only about 4 million solar masses. TON 618 is over 16,000 times more massive. What makes TON 618 so unsettling is its scale and energy output. The quasar emits more light than entire galaxies, and the energy released by its accretion disk is enough to be seen across the visible universe. The amount of matter falling into the black hole is so enormous that it outshines all the stars in its host galaxy combined, sending jets of radiation and plasma tearing through space. This raises fundamental questions about how such an object could even form. Conventional models of black hole growth struggle to explain how TON 618's central black hole reached its size in such a relatively short time after the birth of the universe. It suggests that black holes can grow faster and larger than we thought possible, potentially altering how we understand galactic evolution. TON 618 isn't just dangerous in theory. It represents the upper limit of gravitational consumption, a cosmic monster that dwarfs even the most extreme phenomena. If such an object were closer to us, it would be capable of evaporating atmospheres, tearing stars apart, and warping space on intergalactic scales. Its presence reminds us that in the depths of space, there exist entities so massive and powerful that they stretch the limits of physics and our own cosmic insignificance. The edge of the observable universe. The edge of the observable universe isn't a physical boundary, but a cosmic horizon, a limit set by the age of the universe and the speed of light. Light takes time to travel, and since the universe is about 13.8 billion years old, we can only see as far as light has had time to reach us. But due to cosmic expansion, that distance isn't 13.8 billion light-years, it's actually about 46.5 billion light-years in every direction. This defines a sphere around Earth known as the observable universe. The concept was developed in the mid-20th century, following discoveries about cosmic expansion and the Big Bang. As space itself stretches, galaxies farther away recede from us, faster than the speed of light, not because they're moving through space quickly, but because the fabric of space between us is expanding. What makes the edge of the observable universe so terrifying is what lies beyond it, nothing we can ever know. Anything past that boundary is forever invisible, not because it doesn't exist, but because light from those regions will never reach us. These galaxies and structures are not only unreachable, they are unknowable, permanently separated from us by the expansion of space itself. Even more unsettling is that galaxies near the edge are moving away so fast that their light will eventually stretch beyond detection. As time goes on, these galaxies will disappear from view forever, leaving the universe darker, emptier, and more isolated. This means that the observable universe is shrinking in terms of what we'll be able to see in the distant future. The edge of the observable universe represents more than a distance, it is a barrier to knowledge. Beyond it could lie an infinite expanse of galaxies, unknown forms of matter, different physical laws, or even other universes. We will never know. Not because we lack the technology, but because light and therefore information cannot cross that boundary. It is the ultimate isolation, a cosmic wall that defines the limits of what we can observe, measure, or even imagine. And as the universe continues to expand, that wall will keep moving farther out, pulling the rest of existence away from us into eternal silence. False vacuum decay. False vacuum decay is not a place, but a cosmic threat embedded in the very structure of reality. It arises from quantum field theory, particularly our understanding of the Higgs field, which is responsible for giving particles their mass. According to some interpretations, the universe may not be in its most stable possible energy state, what physicists call the true vacuum. Instead, we may be trapped in a false vacuum, a temporary, metastable state that appears stable but isn't. This idea first gained traction following the discovery of the Higgs boson in 2012. When physicists plugged the Higgs boson's mass, around 125 GeV, and the top quark's mass into equations, the results suggested that the vacuum of our universe might be metastable, meaning it could spontaneously collapse under the right conditions. If that were to happen, a small bubble of true vacuum would form somewhere in the universe and begin expanding outward at the speed of light. This bubble would rewrite the laws of physics inside it, changing constants, particles, and the very fabric of space-time. Any matter it touched, including galaxies, stars, and planets, would be instantly annihilated. Earth would vanish before any warning could be detected. What makes false vacuum decay so terrifying is its total unpredictability and unstoppable nature. It would occur without any signal. There would be no flash, no gravitational wave, no forewarning of any kind. It wouldn't just destroy life, it would overwrite reality. Electromagnetism might cease to function, atoms might no longer bind, and the universe itself could become a cold, lifeless void governed by alien physics. The only reason we continue to exist may be because the process hasn't randomly started yet, or because quantum tunneling events like this are incredibly rare on human timescales. But mathematically, the possibility exists, and it is encoded into the very equations that describe our universe. False vacuum decay is not just the death of a planet or a star. It's the death of everything, everywhere. Instantly, a universal reset, wiping out the cosmos as we know it. Protostar. Stars exist in 8 distinct evolutionary phases, each representing a different stage in stellar development or a specific type of stellar remnant. The journey begins with protostars, the earliest form of stellar objects that have not yet achieved nuclear fusion. A protostar forms when a massive cloud of gas and dust, called a nebula, begins collapsing under its own gravitational force. This collapse occurs over hundreds of thousands of years as gravity pulls the material inward toward a central point. As the gas compresses, it heats up due to gravitational potential energy, converting to thermal energy. The temperature rises from near absolute zero to several thousand degrees Kelvin. During this phase, the protostar generates light and heat purely from gravitational compression, not nuclear fusion. The object glows because the compressed gas releases energy as it falls inward. The protostar continues to contract and heat up until its core temperature reaches approximately 10 million degrees Kelvin. At this critical temperature, hydrogen nuclei move fast enough to overcome their electromagnetic repulsion and fuse together, marking the transition from protostar to main sequence star. The protostar phase typically lasts between 100,000 to 1 million years, depending on the initial mass of the collapsing gas cloud. More massive protostars heat up faster and reach fusion temperatures more quickly than smaller ones. Main sequence star. Main sequence stars represent the longest and most stable phase of stellar evolution, where stars spend roughly 90% of their total lifetime. These stars achieve hydrostatic equilibrium, a perfect balance between the inward pull of gravity and the outward pressure created by nuclear fusion in their cores. Nuclear fusion in main-sequence stars follows the proton-proton chain reaction. 4 hydrogen nuclei combine through a series of steps to create one helium nucleus, releasing tremendous amounts of energy in the process. This energy travels from the core to the surface over thousands of years, eventually radiating into space as light and heat. Main-sequence stars are classified into 7 spectral types based on their surface, temperature, and color. O-type stars are the hottest at 25,000 to 50,000 Kelvin, appearing blue-white. B-type stars range from 10,000 to 25,000 Kelvin and appear blue. A-type stars operate between 7,500 to 10,000 Kelvin, appearing white. F-type stars run 6,000 to 7,500 Kelvin, appearing yellow-white. G-type stars, like our Sun, operate at 5,200 to 6,000 Kelvin, appearing yellow. K-type stars range from 3,700 to 5,200 Kelvin, appearing orange. M-type stars are the coolest at 2,400 to 3,700 Kelvin, appearing red. The mass of a main-sequence star determines its lifetime. Massive O and B-type stars burn through their hydrogen fuel in just 10 to 100 million years due to their extreme core temperatures. Medium-mass stars, like our Sun, maintain fusion for approximately 10 billion years. Low-mass M-type red dwarf stars can sustain fusion for up to 1 trillion years because their cooler cores burn fuel much more slowly. Giant stars form when main-sequence stars exhaust the hydrogen fuel in their cores. As hydrogen fusion slows down, the core begins contracting under gravity while simultaneously heating up. This increased core temperature ignites hydrogen fusion in a shell surrounding the depleted core, creating more energy than the star produced during its main sequence phase. The additional energy from shell burning pushes the star's outer layers outward, causing the star to expand dramatically. As these outer layers move farther from the hot core, they cool down significantly, shifting the star's color from its original hue toward red or orange. A typical giant star can expand to 10 to 100 times its original main sequence radius. Red giants represent the most common type of giant star. When our Sun becomes a red giant in approximately 5 billion years, it will expand beyond Earth's current orbit. The surface temperature drops to around 3,000 to 4,000 Kelvin, giving these stars their characteristic red appearance despite their increased luminosity. During the giant phase, stars with sufficient mass begin fusing helium in their cores through the triple alpha process. 3 helium nuclei combine to form carbon, releasing energy and providing a new fuel source. This helium fusion occurs at temperatures exceeding 100 million Kelvin and creates heavier elements, including carbon and oxygen. The giant phase lasts between 100 million to 1 billion years, depending on the star's mass. More massive stars progress through this phase more quickly due to their higher core temperatures and faster fusion rates. Supergiant. Supergiant stars represent the most massive and luminous stars in the universe. Typically containing 8 to 100 times the mass of our Sun, these stellar behemoths form when giant stars with sufficient mass continue expanding and begin fusing progressively heavier elements in their cores. Supergiants develop a layered internal structure resembling an onion. The core fuses the heaviest elements the star can process, surrounded by shells that fuse progressively lighter elements. The innermost region fuses silicon into iron. The next shell outward fuses oxygen into silicon, followed by shells fusing carbon, helium, and hydrogen in successive layers. Red supergiants like Betelgeuse can expand to over 1,000 times the Sun's radius. If Betelgeuse replaced our Sun, its surface would extend beyond Jupiter's orbit. These stars maintain surface temperatures between 3,000 to 4,500 Kelvin, giving them their red coloration despite their enormous energy output. Blue supergiants represent the hottest and most luminous supergiants, with surface temperatures exceeding 20,000 Kelvin. These stars burn through their fuel extremely rapidly, often completing their entire life cycle in just 10 to 50 million years. Their intense radiation pressure can blow away significant portions of their outer layers, creating spectacular stellar winds. The supergiant phase ends when the star's core begins producing iron. Iron fusion requires more energy than it releases, so the core can no longer generate outward pressure to counteract gravity. This leads to catastrophic core collapse and triggers a supernova explosion. Neutron star. Neutron stars form from the collapsed cores of supergiants during supernova explosions. When a supergiant's iron core can no longer sustain fusion, gravity overwhelms all other forces and crushes the core in less than 1 second. The core collapse is so violent that protons and electrons are forced together to form neutrons, creating an object composed almost entirely of neutrons. A typical neutron star contains 1.4 to 3 times the mass of our Sun compressed into a sphere only 20 to 25 kilometers in diameter. This extreme compression creates matter density of approximately 1 billion tons per cubic centimeter. A teaspoon of neutron star material would weigh roughly 10 million tons on Earth. The surface of a neutron star consists of a crystalline lattice of atomic nuclei and electrons, forming the strongest material known in the universe. Below this crust lies a superfluid ocean of neutrons that flows without friction. The core may contain exotic matter including hyperons, kaons, and possibly quark matter that cannot exist under normal conditions. Neutron stars possess magnetic fields trillions of times stronger than Earth's magnetic field. These intense magnetic fields accelerate charged particles to near light speed, creating beams of radiation that emanate from the magnetic poles. The magnetic poles rarely align with the star's rotational axis, causing the radiation beams to sweep through space like lighthouse beams. Neutron stars rotate extremely rapidly, with periods ranging from milliseconds to several seconds. This rapid rotation results from conservation of angular momentum during core collapse, similar to how figure skaters spin faster when they pull their arms inward. Pulsar. Pulsars are rapidly rotating neutron stars that emit regular pulses of electromagnetic radiation detectable from Earth. These pulses occur when the neutron star's radiation beams sweep across our line of sight as the star rotates, creating a cosmic lighthouse effect. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who initially thought the regular radio signals might be communications from extraterrestrial intelligence. The signals repeated every 1.3 seconds with clockwork precision, leading to the temporary designation Little Green Men 1, before astronomers realized they were observing a natural phenomenon. Pulsar timing is extraordinarily precise, with some millisecond pulsars keeping time more accurately than atomic clocks. The Crab pulsar, formed from a supernova observed by Chinese astronomers in 1054, rotates 30 times per second and has been slowing down at a measurable rate since its discovery. Pulsars emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. The radiation originates from charged particles accelerated along the neutron star's magnetic field lines. As these particles spiral around the magnetic field, they emit synchrotron radiation that forms the characteristic pulsar beams. Over time, pulsars gradually slow down as they lose rotational energy through electromagnetic radiation. Young pulsars rotate rapidly and emit strong radiation, while older pulsars spin more slowly and eventually become too weak to detect. This process typically takes millions to billions of years. Magnetar. Magnetars represent the most magnetically powerful objects in the known universe, possessing magnetic fields quadrillions of times stronger than Earth's magnetic field. These exotic neutron stars form when particularly massive stars collapse, and their magnetic fields become amplified to extraordinary levels during the core collapse process. A typical magnetar's magnetic field strength reaches 10 to the 15th Gauss, compared to Earth's magnetic field of roughly half a Gauss. This magnetic field is so intense it could erase a credit card from 1,000 kilometers away and would be lethal to humans at distances of 1,000 kilometers due to the disruption of nerve impulses. The extreme magnetic field creates a magnetosphere extending thousands of kilometers from the magnetar's surface. Within this region, the magnetic field is strong enough to distort the shape of atoms, stretching them into needle-like configurations. The field also affects the propagation of light, causing photons to split into multiple particles or change polarization. Magnetars experience sudden magnetic field reconfigurations called starquakes, where the neutron star's crust cracks under magnetic stress. These events release enormous amounts of energy in the form of gamma-ray bursts and X-ray flares. A single magnetar flare can release more energy in 1/10 of a second than our Sun produces in 100,000 years. The most powerful magnetar flare ever recorded occurred in 2004 from SGR 1806-20, located 50,000 light-years from Earth. This flare temporarily blinded several satellites and caused measurable changes in Earth's upper atmosphere despite the vast distance. The energy release was equivalent to what our Sun produces in 250,000 years. Magnetars have relatively short active lifespans of approximately 10,000 years before their magnetic fields decay to normal neutron star levels. Only about 30 confirmed magnetars exist in our galaxy, making them among the rarest stellar objects. Black hole. Black holes form when neutron stars exceed approximately 3 solar masses, the point where even neutron degeneracy pressure cannot resist gravitational collapse. At this threshold, gravity becomes so strong that nothing can prevent the matter from collapsing into a singularity, a point of theoretically infinite density and zero volume. The event horizon defines the boundary around a black hole, beyond which nothing, including light, can escape. The radius of this boundary, called the Schwarzschild radius, depends directly on the black hole's mass. For a black hole with our Sun's mass, the event horizon would have a radius of approximately 3 kilometers. Stellar mass black holes typically contain 3 to 20 times the mass of our Sun compressed within their event horizons. These objects warp spacetime so severely that time dilation becomes extreme near the event horizon. An outside observer would see objects falling toward the black hole appear to slow down and freeze at the event horizon, while the falling object would experience normal time passage. The singularity at a black hole center represents a breakdown of known physics. General relativity predicts infinite density and curvature of spacetime, but quantum mechanics suggests this description becomes invalid at such extreme scales. The actual nature of matter at the singularity remains one of physics' greatest unsolved mysteries. Black holes can grow by accreting matter from their surroundings or by merging with other black holes. As matter spirals into a black hole, it forms an accretion disk that heats up to millions of degrees, emitting intense X-rays and gamma rays. These emissions make black holes detectable despite their inability to emit light directly.